So how do we go about applying the idea of slope to a curve like the one that you see in front of you? Let's say, for instance, that we want to figure out what the value of the slope is at the point c comma f of c on this graph of f. All right. So we know that it should be negative. We can see that from the picture. If we were walking on this graph, we would be walking downhill. But what do we need to do? Well, what we're going to do is we're going to play with some things called secant lines. A secant line is a line that passes through two different points on a graph. So let's say, for instance, that I start with some second point over here. And I'm going to call this one c plus delta x, comma f of c plus delta x. So what I'm doing is I'm creating a little bit of a distance here. So this distance here is delta x between the two. And delta x can be positive or negative. I could create points on the other side as well. So I could also pick a different delta x. And let's say I came over here and had some other value, c plus delta x, comma c f of c plus delta x. And that would give me a different value of delta x in this direction. Delta x can be positive or negative. It just gets us somewhere to the left or to the right of the point C. And what we get are secant lines. We can draw a line through a pair of points like this. And since it's a straight line, and all we need is 2 points for a straight line, we can assign a slope to it. So the question becomes, how can we use this idea of secant line to kind of approximate the idea of slope near a point like f of c comma f of c? Well, the smaller we make delta x, the closer those 2 points come together, and the better our approximation should be. So for instance, if I move the green point to about right here, then that starts to look like a better representation of what the slope is. And if I move the yellow point over to, let's say, right here, then that starts to look like a better representation of what the slope is. So what we want is for delta x to be really small. The question becomes is how small is small enough? Well, as you'll see in the definition of a tangent line that's coming up in your lesson, we're going to use a limit and let delta x approach 0. And then the result we get we call the slope of a tangent line. So we're going to end up with the following limit. We're going to consider the limit as delta x approaches 0 of f of c plus delta x minus f of c, all divided by delta x. What we really have on the top here is delta y, the difference in y between the 2 points, where f of c is the y value of the point we're interested in. That's where we're trying to find our slope. F of c plus delta x is the other point that we have, very close to f of c if delta x is close to 0, and we divide by this. This is a 0 over 0 form. If you let delta x go to 0, you'll end up with f of c minus f of c, which is 0 in the top, divided by delta x, which is 0 in the bottom, so it's indeterminate. And if we use proper techniques, we can find that there actually is a value here. So we call this the slope of a tangent line. The radical that you see here, the fraction, is the slope of a secant line. And then when we take the limit, we get the slope of a tangent line. To give you a little bit more of a flavor for what we're doing here, the slope of a secant line is the average rate of change of a function between 2 points. When we add the limit on and let delta x go to 0, we get something called the slope of a tangent line. And the slope of a tangent line is the instantaneous rate of change of a function exactly at that point. So it's not an average rate of change between 2 points, it's an instantaneous rate of change exactly at a given point.